Okay, so this is the idea with infix, is that you always print your left child first, and recursively on your left child, you print out your own value, so root value, and then you recursively call it on your right child. So I recursively call it on my left child, like I say here. I print out my own value, and then I print out my right child's value. And if any of these are null, you just skip that step. So if my left child is null, so if I only have a right child, I just don't do the part which is the recursive call on my left child. Okay, so let's make a more complicated tree so I can see how this works. So binary node, new right child equals a new binary node, 7. Let's set that to be the right of the root. Let's see. Let's make a new tree, which is going to be, or a new branch off of the new left child. So maybe I'll make a right child off of that guy. Set right. I'm just going to create the binary node inside of here. So by the way, I didn't actually have to name this variable if I'm just setting it inside of here. This creates a new one. I just don't give it a name. This one here, root, set right, root? What? No. What am I doing? Okay, new right child. There we go. It was complaining, that underline there, the yellow underline, because I never used new right child. And that was because I screwed up and forgot to set it right here. So what I was saying is that I'm creating a new left child here, which I'm giving a name, setting it in here, but then I don't actually use it again later on. So I could have just created it by setting it within here. So let's actually print this thing out. So if I do system.out.println, and I'm going to say print infix on the root. 252. 252. Where's the 7? Oh, I'm setting this on the right child of the root. I wanted this to actually be the new left child. His right node, I want it to be a 2 as well. Maybe I should make this a different number so I can see it. There we go. So it's printing 2357. Is that right? So my root value is 5. So here, let me make a little commented tree here. So my root value is 5. My left child of my 5 is a 2, and his left child is a 7, or his right child is a 7, so that's the root. And then his right child is a 3. So let's see, if I do this in infix notation, starts at 5, it does print infix on the left, which is the 2. This one tries to call print infix on its left, which doesn't exist, so it prints out 2. There's the 2. And then it calls print infix on its right, which is 3. 3 has no children, so it just returns its root value. 3 is next. So that's the left child of root, is these two. It finally gets back up to here, prints out the 5, which is that. It calls print infix on its right. The right child has no children, so it just returns a 7. I'm done. So this actually will walk through an entire tree and print out everything in infix notation. So when you guys are actually creating your code, you're going to be doing prefix and postfix. And it turns out the only difference is that you're just going to change the order. So if I'm doing prefix, so I'm just going to do this so it stops yelling at me. It's almost going to be exactly the same. The only difference is the order you print the root in. So when you go to prefix notation, you say the root value first. Then you call recursively on left child print prefix, and then print prefix on the right child recursively. Postfix is almost exactly the same thing. It's just that you print the root value afterwards. So when I do postfix, which is also the reverse Polish, you just print the root value afterwards. So you do the left child recursively, then the right child recursively, then the root value. And this is how those engineering calculators actually do it. Strange, I know, but there you go. So I will leave that to you to do the recursive things. It's very similar to Infix. Okay, so now that I have a way to create this stuff, how do I actually make something like an expression tree? So a binary expression tree looks something like this. So I have the various parts of my math. These will be numbers for us, single digit. And then you have plus, minus, times, divide. And this will actually allow you to print out a math expression in prefix, postfix, or infix notation. If we were reading this as infix, what we would do is we would have the left child walk down, so it would be a plus b times c plus 7. And it talks a little bit about this here, by the way. And it actually talks about how these various things are created. So now we need to actually go through and read in something from an infix notation and make it into a prefix or a postfix notation. We don't need to worry about Boolean expressions or algebraic notation or anything like that. We're just going to worry about our basic plus, minus, times, divide. And we're going to assume parentheses as well. So we can deal with that in a minute. So in my assignment, I've actually put in the basic algorithm I'd like you to use, which is this section down here. We're going to be walking through whatever the math expression is and actually printing it out in a particular way. However, this is going to be using something called a stack. You see these things, peek, pop, and push? These are special things that are called from a stack. Stack, Wikipedia. This is an abstract data type. The basic idea. Imagine like you have a stack of plates, kind of like a spring-loaded stack of plates you might see in a cafeteria. The idea is that you can put things on the top, which is pushing them on. You can pull things off the top, which there's this special keyword called pop. Yes, that's using computer science. And you can only get at the thing that's on top. And then whatever's below gets pushed back up as you go. So the basic idea is that you can push as many things on as you want. You can pop whatever's on there, but you can only access this top thing. There's also something called a peek, which is you can look at what's on top. It's the same idea as if you popped it off, looked at it, and pushed it back on. This is actually used for keeping track of a variety of things. Computers use this frequently. We're going to use it to create this expression tree that I was just talking about. We're going to use a node stack. So this is sometimes called a last in, first out data structure. So we need to create one of these in order to actually follow this algorithm here, because we're going to be peeking, popping, and pushing things. So how do we create this? There's a variety of ways we could implement it. Let me create a new class. Node stack. So let's just create a new structure. Node stack. I think I'm going to be using something called an array list to keep track of this. An array list is a lot like an array. It just keeps track of, you don't have to declare the size. You can just keep on adding things to it or removing things from it, unless there's nothing in there. That would be bad. So let's see. I will call this array list of binary nodes stack. You may not have seen this notation before. this less than binary node greater than sign, or if you're used to HTML, you might think of these as tags. This is actually saying what kind of thing I'm going to put in my array list. If you don't put this in, by default, array lists think that you're using something called a capital O object, and you have to actually do some extra stuff, getting things in and taking things out. I happen to know that everything going in here will be a binary node, so I don't have to worry about it. ArrayList is in java.util, so let's import that. And when I create a new node stack, all I say is stack equals new ArrayList of type binary node. And just like any kind of constructor, it's got the parentheses afterwards. It doesn't take anything in the parentheses. This is just the baseline.